Okay, so far we have been talking about distributed computation, right? We have looked at MapReduce, Spark, and Flink, right? MapReduce and Spark are mainly batch computation. Spark also supports streaming by running streams into mini batches. And we have looked at some very cute ideas, right? Immutable RDDs, lineage, re-executing for fault tolerance, re-executing for stragglers, idempotence, deterministic tasks, and so on, right? So hopefully you enjoyed learning about those. But today we will switch gears, right? We will start talking about storage, right? How to store data at scale when things are crashing, but we still don't want to lose data. So in storage, we obviously worry about performance, right? So the rate at which you are able to get the data back, the rate at which you are able to read and write data, right? We worry about that. So to get better performance, we would like to keep things in memory, right? Because disk is slow. But we also have to worry about recoverability, right? So if the entire data center loses power, and when it comes back up, if everything was in memory, we lose everything, right? So for recoverability, we would want to keep things in disk, right? So these are general storage issues that you see even outside of cloud, right? So in a OS as well, you would, for performance, you would want to cache stuff in memory. For recoverability, you would want like some crash consistent file systems and stuff like that. But in distributed storage, we have other issues. So we would really care about availability, right? So your data is split across multiple disks, right? And users are writing and reading to the disks, and these disks can be crashing at any time, right? So we cannot say that the system is now unavailable because a disk crashed. The Amazon cannot sell anything for an hour because some disk crashed, right? So this is very, very bad if this happens, because literally they are earning millions of dollars every hour, right? So you don't want your storage to go away even for seconds, right? So the key idea of availability is basically we would want to hide all the faults, right? So from the client's point of view, the storage is always available, and the general approach to hiding faults is replication, right? So instead of storing your data in one spot, I would want to store it in multiple disks, right? So that even if a disk goes down, even if a data center goes down, hopefully that data is available somewhere else.
This is with the service provider data.
Yeah.
It's a cold storage where they'll keep it.
Right. So replication is a general concept, right? So this is beyond cloud, right? So if you're building your own data center, if you have your 3 laptops connected as a distributed system, right? So this is a general thing beyond a service provider, right? So if you don't want to lose data, do replication. But of course, replication is at odds with scalability and performance. So if I have n disks, I would like n times performance, right? N times throughput and n times the amount of data I can store, right? But if I do lot of replication, then the cost increases, right? Then finally, the other thing we have to worry about is consistency, right? So if reads and writes are happening and there are multiple copies of the data should stay in a consistent state, or the reads and writes should at least see a consistent state, right? So we will spend a little, basically most of our discussion around this, around consistency. So let us see how to define it. So one way to define consistency is you can go inside the storage system and try to reason about consistency, what the storage system is actually doing and stuff like that. But a better way to define consistency is to just see the observable behavior, right? So I have a bunch of clients that are talking to a service, to a storage service, and what are the behaviors they can see, right? So let us say so the strongest form of consistency we would want is to create illusion of a single storage, right? So even though clients are talking to a distributed storage, but we are trying to emulate the behavior of just a single storage, right? So for example, this should never happen with single storage. So to explain this figure, these are different clients, 4 clients that are sending requests. This is where they send the request. This is where they get the response, right? So wx10 means they are writing x equals 10. Rx10 means they were trying to read x and got the value 10 back from the storage system. So if you were talking to a single storage, you would not expect such things, right? So x equals 10 and x equals 20 were written concurrently, right? But then C3 and C4 sent read requests, one at a value of 10 and another at a value of 20, right? So this behavior we would not like. We generally don't expect from a storage system, right? But when you are replicating, these kind of things can happen, right? So let's just look at a very bad storage system which allows such things. So for instance, let us say client 1 and client 2 were talking to two servers, S1 and S2, right? So X is replicated across S1 and S2. And our protocol is client will send its writes to both the servers, right? So C1 is writing x equals 10, so it sent it to both the servers. C2 is writing x equals 20, so it sent it to both the servers. And then reads can happen from any server. So let us say C3 reads 10 because C1 happened to be closer to S1. So WX10 reached C1 before WX20 did, right? So S1 thought that x is still 10, right? So it returns x as 10, whereas S2 thinks that x is 20, right? So it returns x as 20. So this is a very terrible in terms of consistency, very bad design, right? Because it allowed this execution history that you would not expect from a single storage disk. Any questions so far? Okay, so we will first set up a goal for ourselves, right? What do we want to achieve in our storage system that we are looking at today? So we will be studying this system called Raft, right? Raft is widely used. It is key value store under Kubernetes called etcd uses Raft. We have been looking at Redis. The newer versions of Redis now support Raft, right? So it is a widely used algorithm that we will look at today. So what is the goal of Raft? The goal is we want to provide what is called sequential consistency. Right? So, and the way we define sequential consistency is again by looking at allowable histories for the clients. Right? So let us say 3 clients are talking to our storage system. Let us say it first writes 1 and then writes 2. Here it reads 1 and this client reads 2. So any given history seen by clients is sequentially consistent if the if we can identify some points at which the execution actually happened, right? So we can identify certain points where the request actually got committed, right? So this is the point where the system actually wrote x equals 1. And if we can identify these points such that you can draw a linear relationship between them, right? So after this, maybe this happened, and after this, maybe this happened, and after this happened, right? So this history, this execution history is linearizable because we were able to draw this linear relationships among the points at which the operations may have committed, right? So the goal is we should only allow linearizable histories, right? So a history that is not linearizable can never be seen in Raft. And this is our most intuitive behavior, right? We expect our single storage systems to also behave like this, right? So concurrent requests can happen in any order. But if there is a real-time real-time ordering among requests, we would want the system to respect that. So the history we were looking at just now is not linearizable. Right, so the history should respect linear time ordering. So according to time ordering, these happen before writes happened before reads according to real time ordering, right? So this is the time. And then reads should read the latest write, right? So according to real time ordering, WX10 happened before, sometime before RX10, right? But RX10 must have happened sometime before WX20, right? Because we have to read a latest history.
Or WX20 could also have happened before WX10.
Right, so either RX10 happened before WX20 or RX20 happened before WX10, right? So there is no linear order in which we can put these requests to see this outcome, right? That is the point. So just to practice this a little bit more, we can look at another history. WX1, WX2, RX2, and then RX1. So is this allowed? This is not an allowed outcome, right? We cannot arrange them in any linear order to get this execution history. Okay, so this is our goal, right? So this is what is called our safety goal. So safety goals mean that bad things should never happen, right? But we need something else to set up as our target, because building safety is quite easy, right? So let us say I build a storage system that never returns, right? So I have two clients. They were trying to write WX10. This was trying to read X, and this just never returns, right? So this history is linearizable according to our definition of linearizability, right? This storage system is sequentially consistent, but it is pretty useless, right? So safety, and we see this in distributed systems all the time. So safety is about bad things never happen, right? So linearizability is a safety guarantee that bad things will never happen. But at the same time, you would also want liveness, which means good things eventually happen, right? So hopefully the read and write requests are serviced, and you would want liveness across faults, right? So even though systems disks are failing, the storage system is still servicing requests in a way that it upholds your safety requirement. Okay, any questions about safety and liveness?
So what did you say last?
So we would want liveness even though there are faults, so disks are crashing, and while you have liveness, you would want to uphold your safety requirement, right? So bad things should never happen. We should keep servicing read and write requests while upholding safety. Any other questions? Okay, so liveness turns out to be pretty hard. Um, let's look at the reason why liveness is pretty hard. Because let us say you have two servers, S1 and S2, right? These are two replicas of our data. And let us say these are doing some bank-like transactions. So if balance is greater than 10,000, then let me take out 10,000, right? So one client is trying to do this request, and another client is also trying to do a similar request. Right? So both the clients are at ATMs and they are trying to withdraw some money, right? So let us say there is a network partition between S1 and S2, right? So S1 is not able to talk to S2 because the network has some issue. So now from the point of view of S1, S2 is just not responding, right? So S1 doesn't know whether S2 has crashed or whether the network has crashed, right? So S1 doesn't know if the packets are dropping because the network has crashed or because the S2 has crashed, right? So S1 is pretty stuck. Now what to do? So one approach is S1 can assume that S2 has crashed and it can let this transaction happen, right? So it lets you take out 10,000. But at the same time, S2 is not able to talk to S1. So if S2 also assumes that S1 has crashed, then it might also hand out 10,000 rupees, right? So this is a very tricky problem, right? So from the point of view of the server, you don't know whether the other has crashed or whether the network has crashed. And because of this, because we also want to uphold our safety, we cannot make progress, right? So even though we had replicas, we don't have fault tolerance and we don't have liveness, right? We have the data, S1 has the data, but it is not able to service the request because if both S1 and S2 service the request, then bad things will happen, right? So this was thought insurmountable for a long time, right? So this was thought like this is not possible to solve, right? So either you need some external intervention, someone comes and tells S1 that S2 has actually died, so why don't you go ahead and start giving money, right? So basically automated fault tolerance was assumed to be not possible, right, for a long time. But the big idea that actually came out And this is not an idea that came out with Raft. Raft is a more recent paper, but this idea came out in 80s, right, and won a Turing Award. So the big idea that came out is, let's use quorums, right? Use majority, right? So instead of 2 replicas, I will keep 3 replicas, right? And let us say I have a partition. So anytime I can form a majority, I can progress, right? And the guarantee is that you will never have 2 majorities, right? You can never have 2 majorities. So if this side progresses, this side cannot progress because that side cannot form majority, right? So if you have 2f plus 1 replicas, you can be tolerant to f faults because as long as you have f plus 1 replicas still alive in the system, they can form a majority and continue to make progress, right? Okay, so this is the basic setup. Any questions? So our approach to liveness is we will form majorities, right? And our goal on safety is we want linearizability, right? Okay, so now we can start talking about Raft. So Raft is Raft replicates a log, right, to replicate a state machine. So we will see what that means. So the protocol is like this. We have a leader and a bunch of followers, right? Clients only talk to the leader, right? They don't talk to followers. So they say, I want to make k as put value v in the key k. Then leader will put it in a log. Then it will ask all of its followers that append this entry in your log, right? Then followers will append this entry into their log and say that I am done appending, right? So third step is append entries. Then fourth step is I am done appending. As soon as the leader can form a majority, so leader does not need to wait for follower 2. As soon as follower 1 said I have appended the log, I can go ahead and respond to the client, right? So as soon as I have a majority, I can say that I have done servicing your request, right? So this is the general idea of Raft. Right, so basically clients, so we have a bunch of servers, right, and a bunch of clients. Clients are sending requests to the server, right, and this Raft is this consensus module which is going to replicate this log across servers, and then servers are going to apply this log in order to their local state machine, right. So they see x equals 3, so they change x to 3. Once yx1 is committed, they will change y is 1. When y is 9 is committed, they change y to 9. Right. So this is also called replicated state machine. So they have everyone has a state machine, right? Some values to some variables. This state machine can be anything, right? So here we are just looking at a simple key value store, but Redis is also a state machine that supports more complex operations like add something to the set, exec a message, expanding and whatnot. All of that can go into the log, and the state of the Redis will remain consistent across different replicas, right? So this is the goal. This is how the general setup is. So why do we use log? What is the point of log? Yeah, but why log? So the main thing we want to replicate is state machine, right? We want the state machine to be replicated across different servers, right? All of them should think x is equals 3, or the majority should think x is equals 3. But why to use log?
Straggler mitigation, because you only need to write something to the log, not actually.
So straggler is,
So we
right.
we have to maintain multiple state machines.
No,
And
there's only a single state machine.
when we'll use replication, log replication, then we'll maintain multiple state machines for
Right.
multiple states.
So every replica has an identical state machine. We're trying to maintain an identical state machine. Okay, so the point of log is log quite trivially implies linearizability, right? So let us say the clients are sending requests and they are getting responses, right? So these things are put in a sequential log, right? So wx1 will be put in this log, then rx1, then wx2, then rx2, right? So things are running through the log. So because we are replicating the log, we have linearizability, right? Because something comes into the log only between start and stop time, between request and response, and therefore we get a linear order among the requests, right? Any questions? Okay, so this log has to be, so okay, so the goal is this state machine should never diverge, right? We would want to make progress, right? And this state machine should stay replicated across the replicas, right? So the log has to be a sequence of deterministic operations, right? So again, if you have non-deterministic operations, so if I say write x as get time, right? Then when this replica applies this log entry, they may think x is actually 3 p.m. And when another replica applies this entry, they may think x is something else, right? And the state machine diverged. So one of the requirement of Raft is that we would want all the operations to be deterministic, right? So the state machine should be changed in deterministic ways. Okay, so now let's look at the safety property that we need for replicating the log. So basically what we need is that every replica should apply this same log in the same order on the state machine at all times, right? So it should not happen that I did x equals 3 at log index I equals 3 and you did x equals 5 at log index 3, right? So if the two of us applied these logs in a unequal order, then we might end up with divergent state machine, right? So it should not happen that my log looks like this and your log look like that and you committed, right? So if we both of us committed, I will end up with x equals 5 and you will end up with x equals 3. So if the state machine safety says that if I committed x equals 3 at this log index, then every replica must commit x equals 3 at I equals 3, right? Okay, so now we have set up our goal of what we are trying to do. Now we will play with the algorithm and crash stuff and see that we are still able to uphold these safety properties even across arbitrary crashes. Okay, so different clients are sending requests to the log, to the leader. Leader is putting their requests inside the log right? And it is replicating the log on followers. Right. So at any given time, you everyone has a log, right? But only some of them can be committed entries, right? So as soon as I append something to the log, I am not allowed to change the state machine, right? I am only allowed to change the state machine only after I have majority, right? Yeah.
Is the leader the same across different requests?
Leader is across.
Is the leader the same for like across requests? Like can different
Yes.
clients or
Yes.
can it be for
No.
different clients?
There is a single leader. Everyone is talking to that leader in normal operation. But when things crash, we will see when things break. Right. So different. Every replica has their log, and but you are not allowed to commit a log to your state machine until you have majority. Right. So some of these entries may be non-committed entries. Right. That's the notion. Okay, so first let's look at some easy cases. So what happens if follower crashes? If F2 crashes, what will happen? Okay, so just to reiterate, so client first sends the request, leader appends it to the log, then it asks the follower to also append it to their log. Once the follower appends it to the log, they tell the leader that they have appended the entry into the log. When the leader has heard back from majority, it can tell the client that your request is done. Then later, it can say that you should commit this entry because we were able to form majority. Right? So this is the basic protocol. So if F2 crashes, we are okay, right? Because we only have to wait for majority, right? So if F2 crashes, we are fine. If both F1 and F2 crash, then our system becomes unavailable, right? So 2F plus 1 replicas can only handle F faults, right? Because we need a majority to progress. But leader will still try to keep sending append entries request to F2 even though F2 has crashed, in the hope that whenever F2 comes back up, it will rejoin the quorum, right? So it will keep trying to catch up F2 with logs even though F2 has crashed. Okay, so now let us see what happens if leader crashes, right? So clients have been talking to leader, right? And now leader crashes. So our liveness requirement is that we should continue to make progress as long as majority are still up, right? So only the leader has crashed, the followers are still alive, right? So in this case, we have to elect a new leader, right? So the leader has crashed, right? So F2 and F1 will realize that we have not been getting heartbeat messages from leader, right? And they will wait for a timeout. Right? If F1 and F2 has, so every server locally is maintaining a timeout. Anytime it receives a heartbeat, it refreshes the timeout, right? So if it has not received heartbeats for a while, right, then the timeout will expire. And then the follower will become a candidate, right, that I want to become a leader, right? And then it will send a request vote RPC. It will say, I want to become a leader, give me votes. And if F2 gives it a vote, then it will become a leader. Right? So let's look at this behavior. right? So the follower, when you start up, you start in follower. If you have not received heartbeats from the leader, you will time out and start an election. You'll become candidate. If you receive majority, if you receive votes from majority of servers, then you can declare yourself as leader, right? And we will look at others in a moment, other transitions in a moment. Okay, so one thing we would want is what the paper calls election safety. That we should have at most one leader, right? And in bracket, in a given term, we will define term in a moment. So if we have two leaders, the two leaders might both accept entries from client into the log at the same log index, right? And they may try to replicate both of them, right? And we want to disallow letting both of them form majorities, right? So, and so we only want a single leader in a given term, right? So only a single leader is able to form majority, and only a single leader is talking to clients inside a term. Okay, so how does quorum ensures this? That let us say we had 5 replicas. This replica was the leader, right? And this crashed. So then someone will become candidate, right? And so also when they become candidate, they increase the term number, right? So initially this leader was leader for term 1, right? They notice, this guy notices that I have not received any heartbeats from term 1 leader. So it becomes a candidate for term 2, right? And then it requests vote. So it may happen that at the same time this also requests vote for term 2, right? So the reason we have election safety is because there can never be two majorities, right? So it's not possible that it's not possible to form two majorities without a common node, right? And every node can only vote once in a term. So this ensures that we can only have a single leader in a term. Makes sense? Okay, any issues with this? So mechanism of election is election timeout expires, I become a candidate, a follower becomes a candidate. Follower can then ask for votes to everyone it can reach, right? Then a node will either give a vote, or if it has already given a vote to someone else, it will not give a vote. First come first serve basis. So if I get a request vote RPC from you first, I'll just give a vote to you. And the node gives itself a vote as soon as it becomes candidate, right? Yeah.
So what if we have like two followers, one leader has crashed, and F1 gives a vote to F2, F2 gives a vote to F1.
Right. So everyone gives a vote to themselves as soon as they become a follower, as soon as they become a candidate.
So in this, the failed leader also votes.
No, failed leader is dead, right?
Maybe there is some network.
Yeah. So if failed leader restarts, let us say failed leader was not able to send heartbeats, and suddenly it is up again. So as soon as it sees that there is some voting going on for a higher term, it will become a follower, right? Because it was leader for term 1, and it will realize that voting has started for term 2. So it will become a follower, and then it will just act like a follower, give votes.
And for the election safety, suppose one of the follower is not responding, then there might be two possible groups of followers. achieve majority? Two possible candidates.
Right. So what if we have split vote, right? So let us say both of us became candidates at the same time. This node has crashed. I asked for vote here, and it gave vote to me. And this guy asked for vote here, and this gave vote to, right? So no one could form a majority. So no one can become a leader, right? So in this case, there is no leader for term 2, and again there will be a election timeout, and someone else will become candidate for term 3, right? So in a given term there should be no more than one elected leader, but there may be terms where there was no one that could become a leader, right?
But what's the guarantee that even in turn 3 the same problem won't happen?
Yeah.
Right.
Then 2f plus 1 are not able to handle f faults.
Yeah. So what if we just keep doing this forever, right? So I become a candidate, you become a candidate, none of us can build a majority, and none of us can become a leader. Any thoughts? What to?
Arbitrary
It's
piece of
like
work.
it doesn't happen as though in real-time scenario, because whenever there is an election timeout, in case of split votes, at certain point of time there would be a majority.
Leader can
So
appoint
there
like a
would be.
second hand.
Leader can appoint a
Vice leader.
vice leader. Right. Yeah. So the simple solution that the paper proposes is to randomize the timeouts, right? So as long as we make sure all of us are not timing out at the same time, all of us are not starting the request vote at the same time, then hopefully in a couple of terms split vote should go away, right? So what should the randomized timeout be? Right. So what about if the timeout is between 1 millisecond and 2 millisecond? So this is the election timeout. Every node will random, if they have not heard from leader during this election timeout, they will become a leader and become a candidate, right? So what if it is really small? Yeah, so the lower it is, the better it is.
No, but you need to wait for everybody to give the
So
result.
like there might
Huh?
So
be
if the network takes more time and you don't get the result from the others.
Yeah, so leader might still be alive, right? But because you have small timeout, you just declare leader dead and become candidate for the next term. And hope maybe you became a leader and someone else declare you dead and becomes candidate for next term. So the system cannot make progress, right? We just keep doing elections and don't do anything. So what if this is very large, 1 month, 15 days to 1 month?
Then we are stuck with the
Live.
Right, so the leader has been dead for 15 days and we just never noticed it. So for 15 days there is nothing going on, right? So the paper proposes a randomized election timeout between 150 millisecond to 300 millisecond, right? So you want to cover RTTs, right? So you don't want to declare leader dead even though they are alive. So you want the lower range to be higher than RTT. And you want to create some leeway so that split votes don't happen too much, right? If this was 150 to 151, we might continue to get split votes. Right? Okay, so notice that election safety, yeah.
There are 4 nodes and first one got the vote from second and third one got the vote from fourth. Now the timeout of first got over faster and so it asks the vote from third and fourth again. They will not vote because they are still thinking it's the first round. Or how will the others know?
Say that again. So first, So 1, 2, 3, 4. 5 was the old leader that has crashed.
And 1 and 3 are candidates.
1 and 3 are candidates.
1 got vote from 2.
This got vote from 2. This got vote from 4.
Now, first ka timeout was slower, sorry, lesser, so it got timed out faster. So 1 has to vote from 2, 3, 4 again.
Right.
Vote again because the timeout is gone. But
Yeah,
if we
so-
get 4, it's in
No, so 1 will increase the term. Right. So this voting happened for term 2. Right. Every node ensures that they vote once for a given term. Right. So when 1 will become leader again, 3 and 4 are allowed to give votes for term 3. Right. So this will increase the term to 3 and ask votes in term 3. And then they are allowed to give votes.
And what if the leader, before dying, it took some requests, it did not service them, and it died? Now those requests are just gone.
Yeah. So remember, so the question is leader took some requests from client, but it could not build a majority. So those requests are lost, right? And that's actually the desired behavior, right? So you respond to the client only after you have built a majority.
Suppose one machine become a leader and it was in the minority which has the less number of logs, then what will we do to cover the rest of the logs?
Both of them have the same loss. But
In Azure, there are certain minority which might have less logs. So, and this machine supposed to happen in that Azure minority and it became a leader, then how can we calculate that?
Right, that's a very important question, and we will come back to that in a minute after we finish talking about elections. Yeah.
So is it possible that when the candidate asks for vote, it also tells that this is the amount of logs I have?
Right. So we will have to worry about this in a minute, right? Okay, so we notice that election safety says that there should be one leader in one term, right? But it is possible that there are two leaders in the system across terms, right? Election safety doesn't say about across terms. So let us say we have leader L1,
Are you trying to say it will have two states at same time?
two leaders.
A server can be two, like it can be a follower or a leader at the same time.
No. Either a server is a leader or a follower in a given term. So let me just draw this and this will be a bit more clear. Right, so this is still allowed. That in our system, the election safety property says that we should have a single leader in a given term, but we may end up with different leaders, multiple leaders for multiple terms, right? Anyone wants to guess how this can happen? Huh?
Across two terms,
Across terms, yeah. So this guy is the leader in term t minus 1. This guy is leader in term t.
So
right?
basically,
So the L2 died.
No one is dead.
No, L2 died in its previous term, so therefore, like in the next term, L1, it was a follower, now became a leader. Sorry, the other way around.
Yeah.
at T minus
This time
one,
So actually no one had died.
L1 timeout,
L2 did not
so
respond,
L2
so everybody
L1
thought they
dies.
died, and then L2 came back. That
That is
Yeah, so one possibility is there was a network partition, right? So all these three folks think that L1 is dead, right? So they elected a new leader called L2, but L1 still thinks that L1 is the leader for t minus 1 term, right? So some clients will talk to this leader and some other clients may talk to this leader, right? Because clients are only supposed to talk to leaders. Um,
And clients don't know which term it is, right?
yeah,
Client doesn't know whether you are in term T minus 1 or T.
yeah.
So how does a network partition occur?
Just the cable broke,
Like
or someone disconnected a cable. Switch shut down.
so it disconnect like four, like it divides the network into two parts. Like and
No, anything can get disconnected from anything.
like someone can hijack the like connection points and then it connects.
Yeah, like someone just took out the Ethernet cable accidentally, right? So
So the clients are sending the request to all the nodes because in any case,
yeah, so generally when things are up, the clients can send a request to someone, right? And then they will say, hey, I'm not the leader, don't talk to me, talk to the other guy, right? And then they will start sending requests to the leader.
I mean the one that you just pointed to by the follower.
Yes. Okay, so this is okay. Yeah.
Assuming that like all machines are connected to all machines. Like all
Yeah, so replicas know each other, right? Otherwise, they don't know who to ask votes from, right? Is this a problem? This can be a problem, right? Okay, but this is not a problem because L1, so all of these have seen the term T, right? They know that the latest term is T. When L1 tries to commit, it will send append entries and it will tell the term number as T minus 1. It will say that I have a entry to commit, entry to append for the term T minus 1, but this follower will reject the entry, right? So this leader will never be able to form a majority for committing anything because this leader has formed a majority for winning the election, right? And because you can never have two majorities, we are safe. So there should be someone breaking the tie, right?
No, but if there like some of the clients are talking to L1 and some of the clients are
Yeah, so client 3 and client 4 will never be serviced. They will keep sending read and write requests, but L1 is not allowed to acknowledge them because it is not able to form a majority.
What if the T and T minus 1 were split, like L1 and F1 were of T and F2, F3 and L2 had turned T minus 1?
Yeah, so the question is, can this happen that uh,
There won't be an interaction, right? Because it is
so is your question this, that 3 replicas think that the term is T minus 1? So is this possible?
no, it's
No, why is this not possible?
the leader
Yeah, so this leader has gotten elected, right? So the leader can get elected only if majority has given votes. So majority has seen the term T.
So as soon as there is a call for election, the term is incremented.
Yeah. Right, so we can look at the state of every replica, state required for elections, for doing elections. So we want to hold the current term, right? So the replica should remember what is the term, and it should also remember who it has voted for in this term, right? Okay, question for you. Can this be kept in memory or does this have to be kept in disk? Current term and voted for.
this.
Disk. Why disk?
Because if that partitioning, network partitioning kind of thing happened, then you might lose that information.
the states have to be saved, like whatever we are processing. So for that it needs to, because if it is in memory, then it will be lost again. Then we have to again start the execution and again election will be there. So it will be a overhead.
Anyone thinks memory? Do you have a reason?
Memory can be important because it is accessing that frequently. So if it is in disk, it will slow down the system.
Right. So going to disk is slow, right? So we should avoid disk as much as possible. But what if this follower restarts, right? So let us say it had seen. Let me fix this figure. Reset this figure. Right. So this follower had given votes for term t, right? And this follower restarts, right? So now if this was in memory, then it forgot that the term was t, right? And then when it starts seeing a t append entries request from an old leader, it will say, okay, I have appended your entry, right? And that will be a disaster, right? Does voted for need to go into disk?
This could be in memory because it changes after every.
So voted for is for current term. Who did I vote for in current term? Maybe in current term it is null initially. I didn't vote for anyone. But as soon as I hand out a vote, I set who I voted for.
If it is in memory and it restarts, then it could vote to two different.
Yes. So if it is in memory, we can forget who that we had already voted, right? So let us say both of these followers, both of them are asking votes for t plus 1. This guy happily gave vote to L2, and then it restarted and forgot that it had already given a vote, right? And it again gives a vote to L1, right? So we end up with two leaders in the same term and break our election safety, right? So these have to be in disk.
But in terms of current term, we can write simply that which term is greater, just accept that request.
Yes. So you have to remember the latest term you have seen so that you can reject append entries on older terms, right? So you have to remember it across restarts, right?
The current term should be kept in memory because
No, you have to remember the latest term you have seen.
but suppose I have two leaders, one is t minus 1, one is t. Suppose I get request from t minus 1 and I get t from t. I can simply say if t minus 1, since t minus 1 is less than t, I'll accept this for this one segment.
Right, but okay, so the suggestion is I don't need current term in disk, right? So the suggestion is this guy will anyways later see a request from term t, right? And at that point I can start rejecting requests from term t minus 1. So that is a suggestion. But that can break our linearizability, right? So let us say this client said x equals 1 to a later leader. So let me reset this figure again. So this is leader for term. This is leader for term t minus 1. This is leader for term t. So one client said that x is 1. And we happily formed a majority, right, and committed, right? So in our state machine, everyone thinks x is 1. Then we restarted, right? Follower 2 restarted and forgot that it has seen term t. Then this client says that read x, right? But let us assume initial value of x was just 0. So when it restarts, it can let this leader form a majority, right, and let it return Rx0, right, and this will break our linearizability, right. So in terms of the execution, we will see C2 wrote Wx1 and then C3 read Rx0, right, because this was written to leader 2, this was read from leader 1, and the person who was supposed to break the tie actually forgot the term, right? Okay,